So hello. Today we're going to explore the fundamental concepts behind hazards, how we understand them, how we measure them, and so we can manage them effectively. And to start that journey, I need to break down what a hazard actually is. Oh, and by the way, we'll be using the three little pigs to help us along with the story. When we talk about hazards, we're talking about the potential for loss, the things that could go wrong if certain conditions align. Hazards are not accidents, and they're not failures in themselves. Instead, a hazard is a system state. It's a latent source of threat that requires only the right trigger or combination of events to create this unwanted outcome. In engineering, identifying hazards early is essential because we can only manage the risks we have consciously and clearly understood. Now, in the story of the three little pigs, the hazard is simple. The wolf is capable of blowing down the little pig's home. But notice how each pig perceives the hazard differently. The first pig ignores it. The second pig acknowledges it, but only partially. And the third pig clearly fully understands the hazard and designs accordingly. Therefore, understanding your hazards is the foundation of risk management. If we underestimate a hazard, we end up designing something that's inadequate. If we overestimate the hazard, we may waste resources without any meaningful benefit. By making sure we have systematic hazard identification that we'll be addressing later on in the course, using techniques like HAZOPS, SFT, STPA, and FRAM, we're going to gain clarity on these hazards. And once we understand them, we can estimate their risk, choosing the mitigations wisely. Everything begins with understanding what can go wrong. Once we identify the hazards, the next is to understand the limits that our tools can provide us. Remember, unlike physical systems, software failures are systematic. They're not random. This means we can't rely on statistical failure rates in the same way that we can for hardware. The consequence of this has a limiting effect on the way that we can interpret risk and how we can interpret probabilities, which now leads us forwards into discussing quantitative and qualitative methods. Often, when we estimate risks, ideally we have a quantitative probability, a numerical estimate like one failure in a million hours. But in many real systems, especially early in the development or where data is sparse or those the systems that contain software, those numbers simply don't exist. So we need to translate probability into qualitative bands such as frequency, probable, occasional, remote, or improbable. These qualitative representations enable decision makers, even when perfect data is unavailable. The important thing is not the precision of the number, but the relative comparison. It's effectively the application of common sense. Moving from quantitative estimations to qualitative categories helps us frame uncertainty, communicate effectively, and move forwards even if we're dealing with strange and unlimited information. Now note, later on when we meet certain methods, STPA, which is Systems Theoretic Processing Analysis, and FRAM, Functional Renaissance Analysis Method, they deliberately avoid the use of probability in their assessment of risk. Both believe probability is not an appropriate basis for understanding or managing risk in complex, social, technical software systems. Most accidents emerge from complexity, not component failures. Probabilities are unknowable in novel, software-intensive, tightly coupled systems. Both methods focus on causation, not frequency. Risk is addressed quantitatively through systems understanding. In our little diagram here, we have 1, 2, 3, 4, 5, 6 classifications. Each has a likelihood term. You can read for yourself the technical meaning, the colloquial interpretation and my attempt at being witty by addressing weather. Just as we saw that we can classify probability, we can also classify severity. Severity captures how bad the outcome would be if the hazard materialized. That can range from minor inconvenience all the way up to catastrophic loss. Severity classifications help us describe the scale of harm, from negligible through to catastrophic, so we can combine them later on with probabilities. Obviously, the consequence of the associated severity will be context dependent and aligned with the loss perceived by the specific stakeholders. In this example, we have 4 severity classifications with a safety meaning, a colloquial meaning, and yes again, a silly, if not pig-related meaning. So, risk is the product of both probability and severity. Risk is simply the interaction between how likely something is going to happen and how severe the outcome would be if it occurred. The result of this manifests itself as a risk matrix or a risk table. The resulting risk matrix may look a little bit like this. In the top left, we have a risk that is frequent and severe, so is clearly very significant and something we'd want to avoid. This is a risk not worth taking. Bottom right, we have a risk that's improbable and minor. It's so low it can be considered negligible and no concern whatsoever. What's less obvious are the regions of risk in between, and it's those that we need to consider in some more detail. Let's talk about the possibility of a house being destroyed. In this example, it shows an unacceptable level of risk if the chance of your house being destroyed is once in 100 years or more frequent. Well, that risk is intolerable. No cost is too high to reduce it. The advice is this isn't a risk worth taking. Yet, if exceptionally this is something you're considering, then whatever you do to mitigate that risk must not be constrained by anything such as cost and time. Here we have risk at the other end of the spectrum. When the chance of your house being destroyed is around 1 in 100,000 to 1 in 10,000 years, then the risk is low, insignificant, and clearly adequately controlled. The advice is there's no significant risk at all. Just make sure you comply with the standard processes and procedures, and all will be well. Somewhere in the middle, you will make a decision, and that decision is that the risk is tolerable. Tolerable risk falls in a zone where the likelihood and the consequences are concerning, but they're manageable. We'll accept, but only if further risk reduction is not reasonably practical. The advice is this might be a risk worth taking. However, if it's something you're considering, then ensure that the cost of managing the risk is not disproportionate to the benefits achieved by delivering the project over the lifetime of that project. In this very hypothetical risk matrix, I've identified 4 zones. Intolerable, not to be built. Unacceptable, exceptionally, I will allow you to build this, but you'll have to put in place mitigation that clearly demonstrates your ability to manage that risk down to a tolerable level. I have a tolerable zone. Yep, you can build this, but I anticipate there are mechanisms in place to manage that risk. Unacceptable. Happy for you to go ahead without any particular special measurements required. So, what have we done so far? We've explored how hazards, probabilities, severities, and ALARP combine to inform our understanding of risk. Now let's see how these ideas connect with the fundamental safety principles of IEC 61508 and the story of our pigs. Let's have a look at IEC 61508. but it's the foundational standard for functional safety, defining how systems must be designed to reduce risks to a tolerable level. To apply these ideas, we also need to understand the relationship between risk, assurance, and integrity. So, IEC 61508 has the idea of unacceptable, intolerable risk, tolerable if only a large risk, and acceptable, that's broadly acceptable risks. Let's have a chat about risk, integrity, and assurance. Integrity is the confidence we have that a system will perform safely, and that confidence depends upon the assurance provided by the rigor of the engineering process. And this is going to bring us right back to the basics of how traditional constraints shape engineering decisions. The classic project iron triangle illustrates the trade-off between cost, time, and quality. Each of those are influencing project risk. This is beautifully described by a fellow northerner in his iron triangle video that I'm going to provide you for a link. I hope that you're going to watch at least the first 5 minutes, and when you come back we can then focus more directly on risk-related issues. So, we know what the iron triangle is. I'm now going to propose an alternative. In dependable systems, quality should become integrity, and integrity is driven by assurance. How well we can trust the process that created the system will define the level of assurance and therefore the subsequent integrity of the management process or the devices we need to manage that risk. And in turn, assurance itself depends upon 3 crucial factors. Assurance grows when we can see the process clearly, understand what we see, and are able to validate it from diverse viewpoints. So, integrity of an object is proportional to the assurance we have in the process that created that object. The assurance that we have in a process is proportional to the visibility we have of that process. Bottom line, the more we see, the assurance we have in a process is not only related to the visibility, but the assurance we have is proportional to the comprehension of what we see during that process. The more we understand of what we see, the more we're going to trust. And finally, if assurance is related to visibility and assurance is related to comprehension, then to give us additional confidence, the assurance we have in a process is proportional to the diversity of viewpoints. The greater number of views, the greater the level of assurance. Multiple viewpoints from different perspectives build confidence and trust. So, with strong assurance achieved through visibility, comprehension, and diversity, this iron triangle supports a dependable outcome, giving us confidence in the claimed integrity. And this now allows us to move gracefully through to security integrity levels. Because the argument is that the higher safety integrity levels correspond to greater risk reduction. And remembering that software failures are systematic explains why safety integrity levels depend upon process assurance rather than upon any abstract failure rates. If we have a look at this table, if I'm going to be building something where I think that the risk is minor and improbable, then I can use a device that has been certified to be SIL level 1 through a process, through a assurance process that's going to generate an object of SIL level 1. If, however, I'm trying to reduce risk down from severe to frequent, it's obvious now that I need a more significant device. I need a device which is going to have SIL level 4, which itself in turn has been created through a process with a great deal of visibility, a lot of comprehension, and multiple views of reaching the same output. The Three Little Pigs, a safety and risk story. Once upon a time, there were three little pigs who each needed to manage the actual risk of living in an area known to be visited by the big bad wolf. The first little pig decided that the wolf was unlikely to appear and accepted a very high actual risk. He built a house of straw with minimal effort. This house provided very low structural integrity. The house met safety integrity level 1, but it only offered limited protection and only minor risk reduction. In contrast, the second little pig recognized that the wolf was a realistic threat and aimed to reduce that risk a little. He built the house of sticks. This house had better integrity than straw. The actual risk was reduced a little, was still above what would be considered a tolerable risk. This house corresponded to safety integrity level 2, providing partial risk reduction, but not enough to meet the needs of the real threat. The third little pig took the danger seriously. He assessed the actual risk of the wolf and decided it must be reduced to a tolerable level. He worked hard to build a brick house with high integrity, carefully designed to withstand all known threats. The design he came up with followed the Allard principle, reducing the risk to as low as reasonably practical. The house achieved safety integrity level 3, offering significant and robust risk reduction. And, boys and girls, when Big Bad Wolf arrived, the difference in the safety design became clear. The straw house failed immediately, demonstrating its integrity was insufficient and the actual risk had not been reduced at all. The stick house lasted a little bit longer, but still collapsed, showing that SIL 2 protection was inadequate for this particular hazard. The brick house, however, did not fail. Its high integrity assured that the wolf could not blow it down, and the pigs inside were protected because the actual risk had been reduced to a tolerable level and consistent with the Allard principles. Even the chimney had been considered in the safety design, providing additional assurance against foreseeable misuse. After the wolf was defeated, the first two pigs reflected on their poor safety decisions. They recognized that failing to invest in risk reduction had exposed them to an unacceptable risk. They then applied processes with the appropriate level of assurance and rebuilt their houses to SIL 3 standard, ensuring high integrity, strong assurance, and long-term safety. And so, by understanding risk, integrity, assurance, and safety integrity levels, the three little pigs lived happily ever after. Meanwhile, in IEC 61511, each SIL level reflects an increasing requirement for redundancy, self-testing, rigorous development, and documentation to ensure the risk is reduced to acceptable levels. SIL 1, basic safety lifecycle activities. SIL 2, structured methods and some semi-formal techniques. SIL 3, high integrity redundancy formal methods, which you'll be doing soon, independent validation, and systematic fault avoidance, which you hopefully will build into the system. SIL level 4, maximum integrity, highly formalized development, verification, complete independence of the verification and validation. You don't mark your own homework. Very rarely required in practice, but it might be a case of actually not building at all rather than doing SIL level 4. But keep remembering that software failure is systematic. So software SIL requirements in IEC 61508 are framed in terms of the process assurance rather than failure rates. Swiss graph explains how to translate this in practical expectations. It uses some additional parameters: consequence, exposure, and avoidance. So if we have a look at them briefly. Consequence, well, it's the severity of harm that could result if the hazard events occurred. It's quantified as severity levels. And as you can see, we have minor injury, serious injury, irreversible injury, or multiple fatalities. This directly aligns with the severity dimension of risk. Then I have frequency of exposure. IEC often calls this frequency and duration of exposure. The definition: how often people, equipment and the environment are exposed to these hazardous situations. So we're looking at rare to occasional exposure, frequent to continuous exposure. Then we also have the dimension of the possibility of avoidance, the ability to operate the problem when it occurs. It's associated with how fast the hazard develops, whether people can receive warnings, whether escape is possible, whether protective equipment is available and barriers exist. And there are typical scales: possible to avoid the hazard with a timely action, difficult or nearly impossible to avoid it. You can follow the graph yourself and you'll end up at one of a number of possibilities. SIL 1 involves basic certified systems and routine maintenance. SIL 2 introduces self-testing, tighter development controls, rigorous documentation. SIL 3 often requires redesign with built-in redundancy, so no single failure can cause danger. SIL 4, the most stringent, requires multiple layers of redundancy and self-checking. Now, the idea is that these descriptions help make the idea of abstract SILs more concrete. It could get worse. Key ideas that are understanding hazards are measuring risk, applying ALARP, and ensuring process assurance is essential for achieving dependability. These are the key ideas. You need to understand what a hazard is, what actual risk is, tolerable risk is, how to define integrity, and what we mean by assurance. Here, to the three little pigs. So here we go. The moral of the story is that the integrity of the mechanism that you put in place to mitigate the risk is directly proportional to the risk reduction required to reduce it to a tolerable level. This graph explains how SIL maps onto, well, the little pig story. If we have a look, we have consequences, exposure, demand rate, and avoidance. Consequences minor, well, the wolf scares the pigs, but they're fine, there's no damage. Or it's catastrophic, we end up with multiple pigs being eaten. And then we can consider exposure. Well, the pig is only occasionally in the house, or the pig lives in the forest full time, it's his permanent home. Demand rate. Well, the wolf is active, it's persistent, and it repeatedly attacks the houses. Or at the other end of the scale, the wolf is rarely seen, and attacks are exceptional. Then we have the opportunity for avoidance. The pigs can realistically run away, hide, or escape. Or it's possible that the pig is trapped inside the house and must rely upon the house's integrity. And you can apply the graph exactly the same as you could the serious graph. And at the end of this, we'll end up with some particularly good, strong advice to the pigs on the safety integrity level of the houses that they should be building. So, after that meandering story, here is the point. I want you to make sure that you understand each of these terms and concepts so we can use them in both of the case studies. A hazard represents a potential source of harm. It's an inappropriate system state. The actual, unmitigated risk is the combination of the hazard severity and the likelihood before safety measures are applied. The tolerable risk is the maximum level of risk that can be justified on social and regulation grounds. It should be as low as reasonably practicable. Where the actual risk exceeds the tolerable risk, the risk reduction required and the extent of that reduction defines the necessary safety integrity levels of the systems that's managing that risk. Each safety integrity level specifies not only the required integrity, but also the level of assurance, meaning that the rigor of the process, the methods and the evidence required to justify the intended risk reduction has been achieved. Phew. Hope you've had fun, and I hope the pigs are safe. Take care. Bye.